All right, today is the day we get to start going over topic 10 with the 10-1 worksheet. So starting here with number 10, is it always true that two arcs with the same length have the same measure? And explain. No, that's not true, because if we have different sized circles, then that will change the length of the arc with the same angle measure. So we can say no, once I get my Apple Pencil turned on, we can say no. If the circles have different radii, this can happen. If the circles have different radii, this can happen. And we can go ahead and draw a small circle and a bigger circle. And we can say, well, if I have an arc like this on one of my circles, and if I have an arc that same length on the other circle, just going by arc length, you can clearly see that the angle measure will be larger in the first circle than it will be in the second bigger circle. Number 11, Steve is asked to compute the area of the shaded region. What is his error? So he did the area of the segment by doing the area of the sector minus the area of the triangle. However, when he did 90 over 360, he multiplied it by 2 pi r, which is the circumference formula, instead of multiplying it by the area formula of a circle to find the area of the sector. So he used the circumference formula instead of the circle area formula, instead of the circle area formula, which of course is pi r squared. 16 through 19, we're going to find each arc measure. That's pretty simple because arc measure is just in degrees. So if we look at FE, of course, we can see that, hey, that's going to be the same as the central angle measure, which is 100 degrees. If we look at arc BC, that arc is congruent to arc AB. Whoa. And since arc AB has a arc measure of 50, then BC has an arc measure of 50 as well. Then we look at arc CE, and it looks like we have a 90 plus something here. So we have to figure out what is left. And it looks like we know 4 of the arcs in our circle. We're just missing 2. And the 2 that we're missing are congruent. So if I take my whole circle, 360, minus 50, minus 50, minus 90, minus 100, that's all the arcs I know, then I get 70 degrees. And if I divide that by 2, I get 35 degrees. So each of my remaining arcs are 35 degrees, which means the measure of arc CE is 90 plus 35, or 125 degrees. After that, I've got the measure of arc CFE, which again, I know all of these already, so this is pretty simple. So I start at C, and I'm going to go around towards F and towards E. So 50 plus 50 is 100, plus 35 is 135, plus 100 is 235 degrees. Number 20, find each arc length in terms of pi. So if we want to find this arc length in terms of pi, we've got to find the fraction of the circle that we have, which would be 110 over 360 degrees. And we have to multiply that by the circumference of the entire circle, 2 pi r. In this case, the radius is 8. So when we solve this, I would do 2 times 8, which is 16. 16 times 110 over 360. We can kind of do all of that multiplication and division together, and it all simplifies down to 44/9 pi, right? You could also write 44 pi over 9, and that would be the same idea. You could also write that in a decimal form, which would be, I don't know really what decimal that would be, but the decimal equivalent of 44/9 pi. 22 and 23, we're finding the sector area instead of the arc length, which means we're going to do a similar process, but in this case, we'll take the fraction of the circle we have, 52 over 360, multiply it by the area of our circle, pi r times 12, not pi r times 12, I'm sorry, pi r squared. So in this case, that would be pi times 12 squared. And so when we do all of that math, 52 over 360 times 144, that is 104 over 5 pi. And if it says to find to the nearest tenth, that is equivalent to 65.3. Another one here, we have a central angle of 163. So we have an arc length of 163. So we've got 163 over 360 times pi times 9 squared. Put that into the calculator, we get around 115.2 units. All right, let's keep going. Here's some fun ones. Find the area of each segment. And of course, when we're finding the area of a segment, we are going to find the area of the sector minus the area of the triangle. So in this case, the sector is pretty simple because I know that I have a 120-degree angle. So 120 over 360 times pi times 11 squared. And then I'm going to subtract the area. Whoa, I don't know why that keeps happening. I'm going to subtract the area of the sector. So I need to think about how to calculate the area of the sector. Well, I have a 120-degree arc here, which means I have a 120-degree angle. If I divide that angle in half, I actually have two 60-degree angles, which gives me two 30, 60, 90 triangles here. And these are 30, 60, 90 triangles that have a hypotenuse of 11, which means they have a radius of 5.5, not a radius, but a smallest side. And that means that they have a medium length side of 5.5 root 3. Remember, I'm just using my special angle measures here, special triangles, 5 root 3. So if I'm finding the area of the triangle, I'm going to do base times height divided by 2, where that base is 5.5 root 3 plus 5.5 root 3, or 11 root 3, times the height, in this case, of 5.5 over 2, because that's a triangle. And that is going to give me, in this first part, when I simplify this all out, I get 121 over 3 pi. And then in the other side, I get minus 30.25 root 3. And again, you might do your simplifying in a different order or a different way as me, and that's okay. And when I simplify all of this out to the nearest tenth, I get 74.3 as the area of the sector. Or sorry, the segment. This next one, same idea. I need to use the area of the sector minus the area of the triangle. So the area of the sector is going to be 78 over 360 times pi r squared, so pi times 5 squared. And the area of the triangle, that is going to get a little bit tricky. Okay, so I have to find the area of the triangle, and all I know about this triangle is it has a 78-degree angle. And I guess I also know that it is a isosceles triangle, since the radii will be the same. I can find this area a few different ways. but any way I'd slice it, I'm going to need to use trigonometry. So what I've decided to do here is to use the triangle angle process, or the triangle area process that we did in the last part of topic 8, where I'm going to draw a little line that is going to become the height of this triangle. And I'm doing that because I already know that the base is 5. So if I can find the height of this triangle, I can do base times height over 2. Well, let me draw this little skinny right triangle bigger over here so you can see. This little skinny right triangle has a 78-degree angle in the corner and a hypotenuse of 5. If I'm finding the height here, I need to do, let's see, standing on the 78, I have opposite and hypotenuse. That's sine for SOHCAHTOA. So the sine of 78 degrees is equal to x, which I don't know, over hypotenuse, which is 5. 5 sine 78 is equal to the length of x. Okay? So 5 sine 78 is the height of my triangle. So down here, where I already had the area of my sector, I'm going to subtract the area of the triangle, which is going to be base of 5 times height, and I'm just doing this all at once. My height is 5 sine 78. That's this height right here, over 2, because base times height over 2 is the area of my triangle. If I put all this in the calculator at the same time, and if I apply the calculations correctly and put it in, I should come up with 4.8 as my area. No, that's not a rectangle. Let's try it again. There we go. Number 26, the length of curve ABC is 110 feet, arc ABC. What is the radius of circle D? Round to the nearest tenth. So the length of arc ABC here is this length. So we're going to have to use the arc length formula backwards. We'll take the, the arc measure, there we go, over the entire measure. Notice this says arc ABC. That's the major arc here. So the first thing we want to do is 360 minus 54 and find out that our major arc is 306 degrees. So we're going to do 306 over 360 times pi r squared. So times, nope, not pi r squared, 2 pi r. So 2 times pi times, we don't know the radius, we're looking for that, equals the arc length, which they told us is 110. So then I can simplify on the left. 306 times 2 is 612 pi times the radius equals 110. And then I can divide both sides by 612 pi. And I get the radius r is equal to 20.6. All right, let's keep going. This one is pretty tricky. Enrique is selling the drop leaf table and wants to include the area of the table when the leaves are down in his ad. What is the area of the center section when the leaves are down? Round to the nearest square inch and explain how you found your answer. So the way that we're going to want to do this is we're going to want to treat those drop leaves like segments in our circle. So if we start at the center and we draw out the line like this, we're going to treat this drop leaf as a segment of our circle, and we're going to kind of find its area and subtract it from the area of the entire circle. And we're going to do that on both sides because we have two leaves that are the same length. So we're also going to take off this segment right here. How are we going to do that? You say? Don't worry, I'm here to show you. So the first thing that we need to do is we need to say, all right, we would find the area, or sorry, not the area, we would find or need to find the degree measure because we don't have the degree measure. So we can't find the area of the circle yet. Well, we can find the area of the circle. We can't find the area of the arcs or the sectors yet because we don't have the degree measure there. So how could we find the degree measure? Okay, well, one way we could do this is I know about this triangle, all of its side lengths. And the reason I know all of the side lengths of this triangle is because I can find that each of these side lengths are half of 44 inches, since each of them are a radius of the triangle and 44 is the diameter. So each of those side lengths is 22 inches, and the third side is 38 inches. What that will allow me to do is find the angle, the central angle that this leaf makes. How do I find the angle when I know three sides of a triangle? I use the law of cosines. So I'm going to use the law of cosines starting with 38 because it is across from the angle I want to know. So 38 squared equals 22 squared plus 22 squared minus 2 times 22 times 22 cosine of x, the angle we don't know. Right? We solve this. 1,444 equals 22 squared plus 22 squared is 968 minus 2 times 22 times 22 is also 968 cosine of x. Subtract 968 from both sides and we end up with 476 equals negative 968 cosine of x. Then we will divide both sides by negative 968. And when we do that, we end up with negative 0.4917 equals the cosine of angle x. We're almost there. We've almost found the central angle that these leaves make. So then we're going to take the inverse cosine of both sides, and we find that 119.4 equals x. So each of those leaves makes an angle of 119.4 degrees. And that means it makes an arc of 119.4 degrees. So now we can find the angle measure, okay? So we can find the sector area, that whole pizza slice. We can do that. Let me get a different color so I don't run my work into itself. By saying 119.4 over 360 degrees times the area of the circle, pi, times my radius of 22 squared. So that'll give me the area of my sector. Now I need to subtract the area of the triangle. Well, how do I find the area of this triangle? Again, I can use trigonometry. Because what I know is I know that this angle is 119.4. Oops. And if that angle is 119.4, I can do some math. Let me see where I can do this math. I'll do it up here. I can do 360 minus that amount. 360 minus 119.4. And then I can divide that by 2. And what that will give me is the angle measure of each of the remote angles of this isosceles triangle, since they're the same. So I'll take that and divide it by 2. And when I do that, I find that each of those angles is 30.3 degrees. So in each of the corners of these triangles, I have a 30.3 degree angle, okay? And within that 30.3 degree angle, I know some other stuff about the triangle. I know that this side of my triangle is 22 units. So if I'm trying to find the height of this triangle, and I know that each of these side lengths are 22 units, and I know that the angle measure here is 30.3, then I can use the sine ratio, right? If I made a right angle here, I can use the sine ratio to find the length of the opposite side. I can say that the sine of 30.3 is equal to opposite over hypotenuse. That's what I'm going to do. the sine of 30.3 is equal to the opposite x, I don't know the height of that triangle, over the hypotenuse, which is 22. So multiply that, 22 sine of 30.3 is equal to x. And let's go ahead and give that a decimal because we don't want to make this any longer than it needs to be. So we're going to call that 11.099 equals x. That is the height, this piece right here, of each of the triangles made by the leaves. So when I come down here and I'm calculating the area of the sector minus the area of the triangle, now I know the base and the height of these triangles, and I can call the area of that triangle base of 38 times height of 11.099 over 2, because it's the area formula of a triangle. So this is going to give me the area of a sector. When I put this all in the calculator, the area of the sector is the area of the segment. So this is the area of one leaf, is going to be 293.4. It's the area of one leaf. I want to find not the area of a leaf, but the area of the table without each of the two leaves. So I'm going to find the area of the table. That's a fairly simple calculation because that's pi times 22 squared. And I'm going to take off two leaves, two 293.4 leaves. And when I do that, pi times 22 squared minus 2 times 293.4, I come up with 934 inches squared. Whew. There's a whole lot in there, isn't it? That is an in-depth problem. But you know every single thing that you need to do to be able to make that problem work for you and be able to understand it. Number 30, what is the diameter of circle T? It gave us the sector area. So we can use the sector area formula backwards to find the diameter. We can say that we know that 72 over 360 times pi r squared, pi times radius, which we don't know, squared, is equal to the sector area, 64 over 5 pi. Then we can go ahead and simplify this. I'm going to turn 72 over 360 into a decimal and also 64 over 5 into a decimal because I'm just tired of working with fractions. So I'm going to call that 0.2 pi r squared equals, and then 64 over 5 is 12.8 pi. Then I'm going to divide both sides by 0.2 pi so that I can get r squared on its own. That'll also get rid of my pi's. And so that is going to give me r squared on its own is equal to 64. Then when I take the square root of both sides, I get r is equal to, obviously, 8. But this question asks us the diameter of t, not the radius. So at the end, I have to multiply that by 2, and the diameter is 16 units. All right. One more to go. This one is also pretty difficult. Very in-depth problem here. Charlie is designing a dartboard and wants the red sections to be 25% of the total area. What should be the radius of the inner circle? This is a problem that I would usually call an extra credit problem. Okay? So let's think about how this is going to work. He's got a 50 centimeter diameter dartboard. That's going to be really important to us. If the diameter is 50 centimeters, the radius is 25 centimeters. 25 centimeters is going to be helpful. Okay? So I want the red area to be 25% the total area of the circle. Well, I can figure out the total area of the circle here because I can do pi times radius, 25 squared. But I only want a quarter of that circle. So I'm actually going to find the area of a quarter of the circle by doing pi times 25 squared over 4. So the area of a quarter of that circle is 490.5. This means that the red area The red area is 490.5 centimeters squared. So I need to figure out what radius my circle needs to be to give me a red area of 490.5 centimeters squared. So let's model out the area of the red. Okay, so we're going to say 490.5 centimeters squared, the amount we need, if I can write it. I don't need to write centimeters squared there. I'm just going to say that is going to be equal to the area of the red slices, right? I'm imagining that this red is a full pizza slice and it goes all the way to the center. I'm going to find the area of that sector, and then I'm going to subtract the area of all of the inner sectors. So I'm just looking for this red pizza crust of 4 slices of my pizza. And I can do that by first finding the amount of degrees that the red takes up. 65, 65, 65, and 65 tells me that I have 260 degrees of red over 360 degrees of circle. And then I've got the area of that red would be multiplied by the area of the circle, so pi times 25 squared. But then I've got to subtract the area of the inner circle. So I have to subtract basically these little white wedges. These little white wedges have the same area, they have the same arc measure as the red ones on the outside. They have little arc measures of 65 degrees each. So there's 260 degrees of inner white there. So 260 over 360 times pi. The question is right here. What should be the radius of the inner circle? There's where I leave my radius r squared. So we know that the red, if it was a whole pizza slice, minus the white pizza slices, is going to give me 490.5. That is the 25% of the area of the entire circle. So that now I just need to do a bunch of solving. So 260 over 360 times pi times 25 squared. That is going to give me 1,418.08 minus, and then here 260 over 360 pi, I'm just going to call that 260 over 360 is 0.72 pi r squared, and I'm going to go from there. Let's keep this r red because that's what I'm looking for. Okay, and this is still equal to 490.5. So then I'm going to subtract, right? I'm going to subtract 1418.08 from both sides. Oops, I need to keep my colors consistent here. Hold on a second. 490.05 equals. So then I'll subtract 1418 from both sides. And that's going to give me negative 927. Again, want to alternate so we don't lose track of what we're doing. Negative 927 point, oh, I don't know, 0.6. Right? Oops, that's where I made a mistake. I turned 490.5 into 490.05 here. 0.5 minus 1418.08. That gives me roughly negative 927.6 is equal to negative 0.72 pi times our radius that we're looking for squared. Now I'm going to divide both sides by negative 0.72 pi because I want r squared on its own. And when I divide both sides by negative 0.72 pi, I find out that r squared, which is all I have left on the left-hand side, is equal to 410.08. And then, of course, all I need to do after that is take the square root of both sides to find the radius. And our radius, finally, is going to be 20.2. So the radius of the inner circle needs to be 20.2 in order for the red area on the dartboard to cover 25% of the total area of the circle. Super convoluted, but if you're up for the challenge, I want you to take a look and see if you understand how that works so that you can get a good picture of how some of these more tricky problems could be set up. Anyways, there is everything from this section. Let me know what questions you have and I can help you from there. Have a wonderful day.